Hello and good morning or good day. This would be our supplemental video lecture for the course Logic Circuits and Design Theory. And with this video, I'll discuss the different styles or number conversion techniques that can be used to convert the different number systems. So for today's video lecture, we will be looking into the conversion of decimal to binary, binary to decimal, binary to octal, binary to hexadecimal, and we'll also discuss ways to actually convert decimal to any number systems and vice versa. So we will begin first with our conversion from the decimal number system or the base 10 to the binary number system or base 2. So there are actually a number of ways to do this. We'll begin with the conversion of decimal to binary using the continuous division by 2. So let's have an example here. So let's have for number 1, let's have 250. In continuous division by 2, what we will be doing, as the name suggests, is we will be dividing 250 base 10 by 2 continuously until we reach a quotient of 1. So in this method, we will be dividing the numbers by 2 and getting their remainder. And the remainder part is actually the important part in this method because that will be the one that we'll be using as digits for binary. As we are dividing by 2, there are only two possible remainders, 0 or 1. Anyway, so let's divide 250 first by 2. And 250 divided by 2 would be 125, remainder 0. So let's put the remainder here. So that's too large. Okay. So we put the 125 here. Excuse my writing, I'm using my mouse. Hopefully to get a writing pad soon. Now 125 divided by 2 would now be equal to 62 with a single remainder. So we put the remainder 1 here. Be careful in dividing because you might be already used to dividing without the quotient. For example, 125 divided by 2 would be 62.5. So go back to your elementary days where we used to divide manually and we used remainders as a way to show any remaining numbers. Okay, so going on, 125 divided by 2 again would be 62, remainder 1. We have 62 divided by 2 would be 31, remainder 0. Okay. 31 divided by 2 would be 15, remainder 1. Okay. 15 divided by 2 would be 7, remainder 1. So notice we put the remainder next to the number that we're trying to divide or try to divide into 2. 7 divided by 2 would be 3, remainder 1. And then finally, when we divide 3 by 2, we get 1, remainder 1. As mentioned, we would stop the method once we get a quotient of 1. So the only possible final quotient would always be 1. So if you get a different number lesser than 1, then you did something wrong. Okay? So what will be the answer? So 250 divided by or converted to binary. So we just have to follow the last um, answer here, which is 1. It would always be 1. And then we follow it up. So that would mean that our answer will be 1, 1, 1, 1, 1, 0, 1, 0. So let me just put that up. So 1, 1, 1, 1, 1. So that would be 5 ones. 0, 1, 0. And binary. As always, do not forget to put in the base 2 to signify that this is a binary number. Let's have another example. Let's have a simpler example, a 2-digit number. So let's have, let's say 73. Yeah, here we go. And we are to convert this into binary. So 73 divided by 2. As always, we divide continuously by 2. 73 divided by 2 would be 36, I think. Hopefully I don't get this wrong, as it would look stupid on camera. Okay, so remainder 1. 36 divided by 2 would be 18. Remainder 0. Oh, sorry. So remainder 0 here. So we have the 18 here. 18 divided by 2 would be 9. With a 0 remainder. 9 divided by 2 would be 4. With a remainder of 1. And then 4 divided by 2 would be 2. Remainder 0. And then finally, 2 divided by 2 would be equal to 1. Remainder 0. So again, once we reach the final number, which is 1, we actually stop already. So again, we choose the last number from 1, and then we put the number upwards. So 73 base 10 would now, converted to binary, would now be equal to 1, 0, 0, 1, 0, 0, 1 base 2. Okay, now let's have another final example. So to complete our 3 examples here, so let me just move this to a bit to the left. Okay, so let's continue with our 3rd example. So let's have a bigger number this time. So let's have 1,100 as our main example. Let's move this a bit here. Okay. So continuous division by 2. So we'll now have, we'll do this a bit quicker. This is our 3rd example already. So we'll have 550 with a remainder of 0. 550 divided by 2 would be 275. Remainder 0. 275, so 134. Or 137 rather. There we go. Would have a remainder of 1. 137 divided by 2 would be 65. Then we have 3, so 68. With a remainder of 1. 68 divided by 2 would be 34. That would be no remainder. Then 17, 0 remainder as well. 17 divided by 2 would be 8 with a remainder of 1. Okay. Let's move 8 here. 8 divided by 2 would be 4. Remainder 0. 4 divided by 2 would be 2. Remainder 0. Oops, made a mistake. Shouldn't have written that there. Should have been here. So another 0. And then finally we have 1, remainder 0. So again, we stop when we get a quotient of 1. Then we move up, including this one. Okay, so 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0. So let's write that as 1, 3 zeros, 1, 0, 0, 1, 1, 0, 0. Base 2. So that would be our answer for the third example. So that is our first method, continuous division by base 2. Now we're going to try to use the same examples in answering, but using the second method, which is continuous subtraction by powers of 2. Okay, now let's continue with our next method, which is the continuous subtraction by powers of 2. So our first method was continuous division by base 2 or by 2. So in this method, the second method, continuous subtraction by powers of 2, if you're having a hard time dividing numbers into 2 or by half, and you'd rather subtract numbers from one another, then this might be an easier path for you or an easier method for you. So as the name suggests, we will be continuously subtracting. So let's have our first example. So our first example was again 250 as shown here. Okay. So we have 250 as our first example. Okay. So how do we do, or how do we use this method? Or what's the process for this method? So what we do first is we actually list down the powers of 2. So the powers of 2 from 1, that would be 1. Then we have 2, 4. So we'll just do this up until we reach a power of 2 that would exceed or equal to 150. So 8. So what I'm just doing is actually multiplying it by 2 continuously. Then 16. Okay. Just move this a bit. Then 32. 64. 128. And then we have 256. Now, because we've already reached a power of 2 greater than the number that we're trying to convert, we're going to stop listing the powers of 2, and we're going to remove that last power that is actually greater than this one. If it was equal, then we include it, but if it is exceeding or greater than the number, we don't include that. Okay, so what do we do? So we remove 256, so we're left with 128. So what we do is we subtract 250 with 128. Okay. So that would be equal to, so borrow 4 here. I'll borrow 1. So 10, that would be 2, 2, and 1. 122. Now, because we subtracted, or we're able to subtract 128, let's put a 1 here. Next, we look at the next number. Next power of 2 is 64. So if it is smaller than the original number, or the number left rather, then we use that as a subtrahend. So subtracted 64. This would be 1, 12, 8, and 11. So that would be 58. Okay? As we were able to subtract 64, we put a 1 here. Then we use 32 as our next subtrahend. Okay. So this would now be equal to 6 and 2, or 26. As we were able to subtract by 32 again, we put a 1 here. Then up next, the next power of 2 would be 16. So we get a 10 here. We're able to subtract by 16, another 1. Then 8. Okay. Then 8. So we have 2 here. We're able to subtract by 8. Let's put a 1 here. And then 4, we can't subtract 4. Well, we can. We'll get a negative number. But we only subtract an equal or a lesser number. So in this case, this is a larger number. We won't be able to use it. So we put 0 here. The next power is 2. So they're equal. We can use that. And then this would be equal to 0. We stop this method once we reach 0, or once we get a difference of 0. So we were able to subtract by 2, so we put a 1 here. But you'll notice there's still a number left, which is 1, but we're already at 0. So any remaining numbers that were not used, we also put a 0 at the top. So that means this would be our answer. And let's not forget the base 2 here. So 1, 1, 1, 1, 1, 0, 1, 0. Let's check our answer from the first method, if they're the same. And they are. So 5 ones, and then 0, 1, 0. Next, let's have our next example. So this time around, let's have 73 as our example here. So as always, we put in the powers of 2. So 1, 2, 4, 8, 16, 32, 64, and then 128. Well, if you're already sure that the 64 is already the largest power of 2 that won't exceed 73, you can actually not go to 128. But I'm just showing the method just in case you're still trying to get a hold on this method. So 128 already exceeds 73. We won't be including that. So 73 minus 64 would now be 11. Nope, 9. Sorry. Okay. So we use this as a subtrahend, so we put a 1. So this is 9, not 4. So we can't use 32. We can't use 16. But we can use 8. And the answer would be 1. We cannot use 4 and 2, but we can use 1 as a subtrahend. And then we end because we already get a difference of 0. And then we use 1 as a subtrahend, then we get this. And our answer would now be this one here. So that would now be equal to 1001001, which is the same answer as our first method. Finally, let's use it on a 4-digit number, 1100. Okay, so let's now go ahead with our third example. I've written, or let's move it with a bigger space. We'll still use our third example from last time, which is 1100. So as always, we write the powers of 2, and there's a lot of them to reach 1100. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and 2048. So, as expected, there are lots of binary digits that we'll be using, as this is already a large number. Well, if you already know that 1024 will be the closest power of 2 that won't exceed the given, but for the sake of consistency, we still included up to the largest power of 2 that would exceed 1100. In any case, let us remove 2048 and let us use 1024 as our subtrahend. So 1100 minus 1024 would be 76. So let's put a 1 here. We can't use 512, we cannot use 256, we can't use 128, but we can use 64. So 76 minus 64 is 12. Can't use 32 and 16, but we can use 8. And we can use 4. Oops, trying to move it, not right. Just move it downwards a bit. There we go. So we have minus 4, so 0. So we stop as the difference is already 0. The unused numbers or digits here, we put in zeros. So base 2. So technically, our answer would now be equal to 1 3 zeros 1 0 0 1 1 0 0 base 2. Let us check if it's the same as our answer from the first method, which is, yes, the same. Okay? So, again, whatever method you may choose really depends on your preference. As of course, unless they have specifically mentioned what method you should use. At least you already know how to do it with subtraction by powers of 2 and division by base 2. So let's look at the third method. The third method is not really in our lecture. So this is just like a FYI or another information that you could use to be able to convert decimal to binary. So this method is called continuous division by powers of 2. So instead of dividing by 2, we're going to use the powers of 2 as a way to divide the numbers. Okay. So let's now go into the third method, which is the continuous division by powers of 2. So we'll use our 3 examples again to try and see and show that they actually have the same result. So for our number 1, we had, let me just check, so 250, 73, and 1100. So let's use 250 first. So in this method, we will be using powers of 2, not 2, to divide the numbers. And we would still get the quotient and the remainder. So we use the largest divisor, or the largest power, as a way to divide it. So for example, we have 250. So we list again the powers. From our example last time, the highest would be 128. So we're going to use 128 as our divisor here. So just fix this up a bit, sorry. So we have 250, then we divide by 128. So 250 divided by 128 would be equal to 1, with a remainder of around 122, something like that. So we 122. So we put the remainder here. So next we use the next largest number. As we were able to divide by 128, let's put a 1 here. Then let us divide by 64. It's similar to continuous subtraction by powers of 2, but doing with a different, or using a different algorithm or method altogether. So 122 divided by 64 would be 1. The 1 here. And the remainder would be around 58. Just verify that it is indeed 58. So 50, 60, 110 plus 4, 8, 122. Okay. Then we can divide by 32. So divided by 32, we have 1 again, with a remainder of 28, no, not 28, 26. Okay. So we were able to divide by 32. Oops, let's use red here. Then divide by 16, which is the next digit, largest or smaller digit here. So we have 1, and we have 10. So we have 1 here. 10 divided by 8, we have 1, with a remainder of 2. So we won't be using 4, but we'll be dividing by 2. And 2 divided by 2 would be equal to 1, of course. Oops. With a remainder of 0. So in this method, we stop when we get 0. So we're not able to divide by 4, so we put a 0 here. And because we were able to divide by 2, we put 1 here. Okay. And then we stop because we have a 0 here. So let's check with our previous example. 5 1s 0 1 0. Okay, so 5 ones, 0 1 0. So it's the same answer. Okay. So we stop when we have a remainder of 1, either a remainder of 1, then we divide by 1 the remainder. We stop when we have a 0 as a remainder. Okay, so this is for our first example. For our second example, we will be using 73. In my opinion, this is a harder method, but at least you'll be equipped and you know that there are other methods around. So we have 73. And the largest one before it exceeds will be 64. So let's just put 1, 2, 4, 8, 16, 32, and 64. So the largest one to divide first would be 64. We get a remainder of 1. Oh, no, a quotient of 1. But we don't need a quotient. What we need is so we're able to divide by 64. So put there here. And the remainder is actually much more important. 73 divided by 64 would be 9. So we can't use 32 and 16, but we could use 8 as a divisor. So we get 1, remainder 1. Just erase this. Looks like 2. We're able to divide by 8. We won't be able to divide by 4 and 2, but we will be able to divide by 1. Get 1, then we stop because the remainder is 0. So we're able to divide by 1. Base 2. And this would be our answer. 1 0 0 1 0 0 1 base 2. Let's look here. It's the same. Yes, 100 101. Same with this one. Let's put a box on this one as well. Let's not forget the base 2 here. Oops, didn't mean to do that. And finally, let's use 1100 as our final example. Okay. So, so 1100. From our example a while ago, 1028 would be the largest power of 2 that we could use here. So let's have enough space to write that. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and finally 1024. Okay. So we can divide by 1024. We get a quotient of 1. We put 1 here as we were able to divide by 1024. The remainder would be 76. So can't use 512, 256, 128, but we can divide by 64. So let's do that and divide 76 by 64. We get 1, and then we have a remainder of 12. Okay. So we can't use 32 and 16, but we can use 8. It's a divisor. So we get 1. Okay. And a remainder of 4. So yes, and we can use 4. Divided by 4, we get 1 with a remainder of 0. Of course, we stop. We still have 2 remaining numbers, or powers of 2, which is 2 and 1. but we just put zeros here. Okay. Let's put zeros. And base 2. Let's not forget about that. And you have this well-written answer here, if I say so myself. Let's go ahead and check that out. 1, 3 zeros, 1 0 0, 1 1 0 0. So here, yep, and here. Yes, confirm. Okay. Among the three, this is the most complicated, and I don't know if you really want to use this, but again, at least you're equipped with that third method. From my experience, students usually choose the first or the second method because they either have an easier time dividing by 2 or subtracting. So that will be all of our examples for conversion of decimal to binary. Then we'll do a reverse process in which we convert binary into decimal. Okay, let's now go to the reverse process by converting a binary number and converting it back to decimal. So we'll use the answers from our examples to make sure that we'll be able to convert it back to the correct answer. So let me just get the answers here. What was that? So we have 5 1s 0 1 0. Okay, let's use that. Oops. So 5 1. So for our first example, we have 1 2 3 4 5 and 0 1 0. So 0 1 0. Okay, so with this method, instead of actually, we're going to reverse it. So we're going to use the continuous addition by powers of 2. Okay. This method originally actually came from the place value method, which is technically the true method of conversion of any number systems into decimal. So we'll show that first, and then this addition of powers of 2 is actually the shortcut method for that. Well, basically what the place value method does, as we have done in our elementary years, okay, is that every position in the number represents a value, hence the name place value. Okay, so for instance, this 0 here, so we just write the numbers downwards. Okay, so we have 0 or the digits, then 1 0, then we have 5 1s here. Okay. We actually multiply them with the place value or the value of each location. So this one, or this first position, is actually means it has a value of 2 raised to 0. Second digit is 2 raised to 1, 2 raised to 2, so on and so forth. So 3, 4, 5, 6, and 7. Okay. Now you'll notice that I use 2 here as a base. That's why it's actually called base 2. If you can remember from the place value discussion for decimal numbers, we have the same method, but we actually use 10 here because it is actually base 10. Okay, so let's simplify this a bit, because the 2 raised to 0 up to 2 raised to 7 and beyond are all part of base 8. So we'll have here, let's just rewrite again, the 0, 1, 0, then the 5 ones. And they're actually multiplied okay, actually multiplied by the powers of 2. So 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4. You can see a pattern here emerging. This is actually our powers of 2. 16, 32, 64, and 128. Okay. Then we get the product of each of those numbers. Automatically, those that has a 0 digit would have 0 as the answer, and those that have 1s would retain their number. 32, 64, and 128. So we have what we have left here. So we just add all of them together. Okay. So let's use our calculator here. So we have 2 plus 8 plus 16 plus 32 plus 64 plus 128, which gives us 190. That, which can't be right. Just go ahead and check. Sorry. So 1, 2, 8. So 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. So let me just 1, 2, 8 plus 64 plus 32 plus 16 plus 8 plus 2. Okay. Might have missed a number there a while ago. So our answer would be 250 base 10. For base 10, we don't have to put 10 here, because any number without a base written is understood to be base 10, or the decimal number system. And to check, it is indeed 250. So officially, this is the actual method, or the place value method, in converting binary to decimal. The good thing about the place value method, we could use that method to actually convert any number values back to the decimal numbers. Okay? But for binary, we actually have a shortcut which still revolves around this method. So it's actually a simplified method of the place value method. So let me just go ahead and go a bit downwards here. So let me just rewrite the number. So 1, 2, 3, 4, 5, 0, 1, 0. Base 2. Okay. Now, what I'm going to do is, instead of doing this place value method, I just go directly to the top or the bottom of the number, binary number, then I just put the powers of 2 there. 16, 32, 64, and 128. Now what I'm going to do is actually add all the numbers that has 1s at the bottom. So that would be 128 plus 64 plus 32 plus 16 plus 8 plus 2, which is basically this right here. 128, 64, 32, 16, 8, and 2, which we already know leads to 250 base 10. Just the same. Okay? So hopefully you understand how we were able to use the continuous addition by powers of 2 as a replacement, as a simplified version of the place value method. Let's do the simplified version with our other examples. So let's have now our number, oopsie daisy, let's have our number 2 here. And number 2 is 1001001. So 1001001. Powers of 2 at the top. 1, 2, 4, 8, 16, 32, finally 64. Add all the numbers with ones on them. So that would be 64 plus 8 plus 1, which would give us 72, 1, 2, 4, 8, 16, 32. So 64 plus 8 is 72, so 73. Is that the same? Looks different. Oh, it is 73. So that's correct. Sorry about that. So we have our correct answer here, which is 73. Then finally, let's have our third example. This time using our last example here, which is 1 3 zeros 1 0 0 1 0 0 0. Hopefully you can remember that. So 1 3 zeros, 1 2 zeros, and 2 ones 2 0. Verify that. 1 0 0 0. Yeah, that'll be correct. So let's just put the powers of 2 at the top. 1, 2, 3. Oh, no. Stupid me. Stupid mistake. 4, 8, 16, 32, 64, 128, 256, 512, and 1024. So we have 1024, 64, 8, and 4. Let's add them all up. 24 plus 64 is 1088 plus 8, 1096 plus 4 would be equal to 2100. Yes. So this would be the same answer here, 1100. Okay. So there are actually other methods to do this, but this is by far the simplest one and easiest to follow. Okay. So next time around, we'll use these numbers to actually convert binary to octal and then hexadecimal numbers. So now let's go into the conversion of binary numbers into octal and hexadecimal. From our discussion, we already showed some few examples. So let's just give a few more examples here. There will be a lesson on the significance of the octal and hexadecimal numbers in logic circuits, but for now, let us learn how to convert binary to octal. So let us use our examples from last time as always. Oops, let me just go ahead and check what are those. So 51010, okay. So for number 1 here, so we have 5 ones, then 0, 1, 0, base 2, to be converted to octal. With the octal number system, as discussed, it only uses digits from 0 to 7. So in conversion of binary to octal, we actually divide the number into groups of 3 bits. So that means from the right. So we have 1, 2, 3 bits here. 1, 2, 3. This one only has 2 bits, so we add a 0 here to make it 3. So if there are any missing, or the number of bits lacks to create a group of 3, we just add zeros. Once we have grouped them into 3, we actually put in powers of 2 at the top, but only up to 4. So 1, 2, 4, 1, 2, 4, and 1, 2, 4. Okay, so now once we have written the powers of 2 up to 4 there, we only add the digits which only has a 1 on them. So like this one. The 1 is only found at the 2, so this is 2. This one has 3 ones, so we have 7. 4 plus 2 plus 1 is 7. This one has 2 and 1. 2 plus 1 is 3. So therefore, our answer is 372 base 8. Let's have the second example. Just go ahead and take a look at that. Where's our... There we go. 100, 1001. Okay, 100, 100, and then 1. Base 2. From the right, group the bits in by 3s. This is only 1 bit, so I add 2 zeros here. Put 1, 2, 4 on each of the bits. Then we add those that have 1s on them. So 1 on the 1, just 1. Another 1 here, and another 1 here. So that means the answer is 111 base 8. Now finally, we have our third example, which is 1000, 100, 1100. So okay, 1, 3 zeros, 1, 2 zeros, 2 1s, 2 zeros, base 2. Well, you guess it, we group it by 3s. This one is missing a number, so we put in 0. We put in 1, 2, 4 at the top. We use those that has 1s at the bottom. So we have 4, we have 1, we have 1, and we have 2. So the answer is 2114 base 8. So it is really not that difficult to actually convert binary to octal. Same with converting binary to hexadecimal, and they're actually quite similar. So let's just go ahead there. So let's put in binary to hexadecimal. Okay, so binary to hexadecimal, instead of grouping the numbers by 3, we group them by 4. Okay, so let's use the same numbers here. 0, 1, 1. So 1, 1, 1, 1. Oh, so we have 5 ones here. And 0, 1, 0. 0, 1, 0, base 2. As our first example. So what do? So we group them by 4 bits. So we have 1, 2, 3, 4, and 1, 2, 3, 4. Just like with conversion to octal, we add additional bits of zeros if the number of bits are not enough to create a group of 4. We put in powers of 2 at the top, but this time we put in up to 8 instead of up to 4. Then we use the ones again. So 8 plus 2 is 10, but we are using hexadecimal. And from our discussion, 10 is A. Okay. Then we have 8, 4, 2, 1. So 8 plus 4 plus 2 plus 1 is 15. So the best way to actually do this is by actually adding all those numbers, 8, 4, 2, and 1, and 15. But how do we remember that what 15 in hexadecimal is? So I've mentioned this in our lecture. What you actually do is you actually try counting, like how you count when you were quite young. You start with 1, 2, 3, 4, 5, but instead of having your fingers as 1, 2, 3, 4, 5, your first finger is B, second finger is C, D, E, and F, up until you have 5 fingers in total. That would represent 11, 12, 13, 14, and 15. Again, A is 10, so we don't start with A, we start with B. So B, C, D, E, and F. So I'm now holding up 5 fingers, which is 15. So that would be F. So our answer would be FA base 16. Next, let's have another example here, which is 1, 0, 0, 1, 0, 0, 1. So 1, 0, 0, 1, 0, 0, 1. Group them by 4. 1, 2, 3, 4 slash 1, 2, 3. It lacks 1 bit. We put in a 0 as a filler. Put in 1, 2, 4, 8 as a way to be able to compute this. So we have 1 and 8, which is 9. And we have 4. So the answer is 49 base 16. 49 base 16 is different from 49, the decimal number. So please do not get confused with that. And our last example would be example number 3. Oops, not that one. Which is 1, 0, 0, 0, 1, 0, 0, 1100. Yeah. So 1, 3 zeros, 1, 2 zeros, 2 ones, 2 zeros, base 2. Group them into 4 bits. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. Add a 0 as a filler to have 4 bits. And we add 1, 2, 4, 8 at the top. So 1, 2, 4, 8, powers of 2. So we'll be using this to add bits as well. So we have 8 and 4, that will be 12. So we count B, C. So 12 is C. Then we have 4 and 4. So our answer would be 4, 4C, base 16. Let me just erase C here. And then box that out rather. So we have 4, 4C, base 16. So binary to octal and binary to hexadecimal is actually quite easy compared to the hour conversion systems. So we will now go with our last part of the discussion, which is converting any number system or any decimal or decimal to any number system and vice versa. We will be using, the main methods we'll be using is the place value method for converting any number system into decimal, and we'll use the continuous division method with the any number system into decimal. Okay, so we will now go into the discussion in which we will be converting any number system into decimal. So we'll be using number systems aside from base 2, base 8, and base 16 to show you a general way of converting decimal to any number systems and vice versa. So let's try converting a number from base 3, meaning it only has 3 values, or 3 symbols rather, 0, 1, and 2. So let's have a 3-digit number of base 3, 1, 2, 0, base 3. The 3 is the base. Okay? And we're to convert this into decimal numbers. So we'll be using the same method, or the place value method we used initially for converting binary to decimal. Okay? So we put in the digits here. So we have 0, 2, and 1. We multiply them with base 3, because this is base 3, so we have 3 raised to 0. So it always starts with 0. The only difference is the base, because this is base 3, we use 3 here. For binary a while ago, where is that? It's missing. Here. So we use 2 as the base, but the exponent starts with 0 and also incrementing by 1. Okay. Going back here. So we have 3 base 1. Oh no, 3 exponent 1 and 3 squared. Further simplification would show us 0 times 3 raised to 1 is 1. 2 times 3 raised to 1 is 3. And 1 times 3 squared is 9. Well, 3 squared is 9 rather. So what we have is 0 times 1 is 0. 6, 2 times 3 is 6. 1 times 9 is 9. We add them all up, and we get the answer of 15 base 3. Okay? So this is, oh no, not base 3. We already converted it to decimal rather. So that is, so 120 base 3 is actually equal to 15. Let's use a different example. This time, let's use base 4. So base 4 has 4 symbols, 0, 1, 2, and 3. Let's have a 3-digit base 4 number. So 2, 3, 1, base 4. Let's try to convert this to decimal. Again, we use the same lines here to make the numbers from horizontal to vertical. Write those digits up, downwards. So it's the same, 231, 132, 132 downwards. We multiply them with base 4 with incrementing exponents. So 4 base exponent 0, 4 exponent 1. And then we have finally 4 squared. We simplify them a bit. 4 raised to 0 is 1. 4 raised to 1 is 1. Oh, no, 4 rather. 2 raised to 2 times 4 squared. 4 squared is 16, which is 4 times 4. We get the product. 1 times 1 is 1. 3 times 4 is 12. 2 times 16 is 32. As mentioned, we add all of them together. We find the summation. So this would be 5 plus 4. Yeah. So we now have 45 as the converted number from 231 base 4. So it has a pattern. The only thing that changes here would be the base, which really depends on what base the number came from. But technically they're the same. It has incrementing exponents from 0 onwards. So if it has a fourth digit here, you'll have 3 raised to 3. Or in this case, in number 2, there's a fourth and fifth digit. You'll have 4 raised to 3 and a 4 raised to 4. Then you just have to complete the computation. Let's have one last example here. This time around, we'll use base 5. Base 5 has 5 symbols. So we can only use 0 to 4. So let's have 5, 3, 2, base 5. I made a mistake. 5 is not part of the symbols. That's a common mistake that students did or do. As you can see, I already did it as well. Made that mistake. So 4, 3, 2, base 5. Convert them into a vertical position. 2, 3, and 4. So we have 5 raised to 0, 5 raised to 1, and 5 squared. So let us simplify that. 5 raised to 0 is 1. 5 raised to 1 is 5. And 5 squared would be 25. Okay. So this would be 2, 15, and 100. We add them. So we'll have 117. So that means 432 base 5 converted to decimal will be 117. We're going to use the same examples, 15, 45, and 117, and we'll try to reverse the process. So we'll convert these decimal numbers back to 15. We'll try to convert it to base 3, 45 to base 4, and 117 to base 5. To show you the process of how we do this. Okay? So let's go ahead. Now, how do we proceed with converting decimal number to any number system? So we'll use a similar idea from the binary or decimal to binary conversion, in which we continuously divide by the base. So if you can remember, we divided it by 2, and then we put in the remainder. So that is how we're going to proceed with this one. Okay. So let's have our first example, which I forgot. So we have 15. Okay. Convert it to base 3. So what we do is we continuously divide by 3, or the base. Then we put the remainder here, we put the quotient here. We stop until the last digit is lesser than the base. So if for some reason the last bit is 2, 1, or 0, then we stop. But it's actually really only 2 or 1. It won't be 0 actually. So 2 and 1 only. So if we divide 15 by 3, we get 5. Remainder 0. If we divide 5 by 3, so 5 divided by 3 would be 1, remainder 2. Okay? Because the last answer is already less than 3, we stop. Just like with binary, we use this as our first number, then we count upwards. So 1, 2, 0, 1, 2, 0, which is our original number. Next, let's convert it's that number again, 45 to base 4. So where is that? Here we go. So 45 convert to base 4. So how do we convert 45 to base 4? So same method, but instead of dividing by 3, we divide by 4, get the quotient and the remainder. Remainder here, quotient here. So 45 divided by 4 is 11. Remainder 1. 11 divided by 4 is 2. Remainder 3. And because the last digit is already less than 4, we stop. As mentioned, we stop when the quotient is lesser than the base itself. So because it's 2, we stop. So the answer would be 2, or this is our first digit going upwards, 2, 3, 1, base 4. Let's check if it's the same. And what do you know? It is the same. Last example. Oops. It's already a bit of lag, as there's already too many handwritings here. So 432 base 5. No. That should be the answer, but what would be the... So it's 117. Okay. So for number 3, we have 117, convert it to base 5. 117 here. Okay. So we divide 117 by 5. So that would be 3. Nope, not 3. That would be... How many 5s are there? 20 times 5 is 100. So 23. So we have 23 with a remainder of 2. Okay, because 23 times 5 is 115 plus 217. Next, how many 5s are there in 23? We have 4 with a remainder of 3. Because the last quotient is lesser than the base, we stop. So the answer is 432 base 5. Okay. Which is the same as this one, 432 base 5. So you can do this in any number systems. You just have to follow our pattern and just make sure that you divide the numbers carefully and get the quotient correctly as well. And so that wraps up our supplemental discussion for number conversions as our initial discussion for the course Logic Circuits and Design. Okay. If you have any questions, feel free to leave it at the comments. I might have missed any mistakes. Kindly write that up at the comment section as well. If you like the video, please do subscribe and leave a like as well. Thank you very much and have a great day.